Example 5. Find the limit of each. Draw the graph of the function. So if we look at part A here, we have the limit of 1 plus 1 over x squared as x approaches 0. So for all of these, we're going to use a graphical approach. So let's think of f of x equaling 1 plus 1 over x squared. Okay, so let's try to graph this function. We should be able to recognize that this is a parent function. Okay, and we should know that this 1 plus shifts that graph up 1 unit through transformations. So notice that for this function, the vertical asymptote would be x equals 0. Because if you had 0 for x, that would make the denominator undefined. For the horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, the horizontal asymptote would be y equals 0. But since the whole graph has been shifted up 1 unit, this is actually going to be y equals 1. Okay, so I'm going to draw the horizontal asymptote here, and I'll draw the vertical asymptote there. Then I can use a table and pick points to the left and to the right of the vertical asymptote. So if I look at the vertical asymptote, if I pick a point to the left of the vertical asymptote, I could try -1. When I plug -1 into the function here, I'm going to get 2. So the graph on this side of the vertical asymptote is going to look like this. And then on the right side of the vertical asymptote, I can pick an x value over here. I'm going to pick 1. If I plug 1 into the function, I'm going to get 2 again. And the graph would look like this. Now we're going to evaluate this limit by looking at the graph. And we're going to do this by looking at one-sided limits. So let's first look at the limit of this function as x approaches 0 coming from the right. Coming from the right, this is obviously going towards infinity, so this is going to equal infinity. And then if we look at the limit of this function as x approaches 0 coming from the left, again, this is going to equal positive infinity. Because both of these one-sided limits equal infinity, this limit overall equals positive infinity. Let's look at part B. Okay, this time we're going to take the limit of this function as x equals 1 coming from the left. Notice this time this function here, this is a pretty complex function. So what I can do instead, I can break it up. I can say, let's let g of x equal x squared plus 1, and let's let h of x, the denominator, equal cotangent of pi x. So first of all, let's graph the function x squared plus 1. Okay, this is going to be a parabola. Okay, and typically, you know, the vertex would be 0, 0 if it was x squared, but it's plus 1, so it's going to be shifted up 1 unit. You're also going to have a point here and there, and up here and there. Okay, you could do this by plotting points as well. But that would be the graph of that parabola. Okay? And what we're going to do here, we're going to take the limit of just g of x. Or let's look at it this way. So you can see it. I'm going to do the limit of x squared plus 1 as x approaches 1 from the left, and divide that by the limit of cotangent of pi over x as x approaches 1 from the left. Hopefully you can see how I decomposed this limit here, broke it apart, and how it's equivalent to the original limit. So the numerator, when I approach 1 from the left, that's going to be equal to I'm sorry. Let's do this. So when I approach 1, oh man, messing that up again. When I approach 1 from the left, it's going to end up being 2. A point there. Okay, now let's try to graph cotangent pi of x. So again here, let's talk about the period of the cotangent function. Let's represent that by t for period. Okay, typically the period for the cotangent function is pi divided by b, where this coefficient in front of this x is going to be b. So if we want to find the period here, it's going to be pi over pi, which would be 1. So what this tells us is this cotangent function here, cotangent of pi x, the period, instead of being pi, it's now going to become 1. So let's graph that. Okay, we're going to have a vertical asymptote here. Vertical asymptote here. And we're going to have a vertical asymptote here. And then you should remember from your trig class that the cotangent function is going to look like this. And it's going to repeat itself. Okay? And then this time, we want to take the limit of cotangent of pi x as x approaches 1 coming from the left. So this is going towards negative infinity. So we're getting 2 over negative infinity. Well, this is just bad notation. That doesn't make any sense. We have to figure out what is this equivalent to. Well, if you think about negative infinity, think if you took 2 and divided that by negative 100. You'd get a pretty small number, right? What if you took 2 and divided it by negative 1,000? You'd get a smaller number, right? Because this is negative infinity. What if you took 2 and divided by negative 10,000? The number would be smaller, and it would just continue to get smaller, which this is telling us that this is actually, and you can put this in your calculator to see this, this is going towards 0. Okay, so we're not going to write this 2 divided by negative infinity. What this really represents here, this really represents 0. All right, let's look at part C. Part C, first of all, let's rewrite this limit. So it's 3 times the limit of the natural log of x as x approaches 0 coming from the right. So we want to graph the natural log function. Okay, so let's start with when x is 1. So if I have y equals the natural log of 1, okay, the base here is e. This is a natural log form. If I put this in exponential form, the base would be e, the exponent would be y, and this would be equal to 1. If this is the case here, hopefully you can see here that y would have to be equal to 0, because anything to the 0 power is 1. Okay? Next, I would want to try y equals the natural log of e. So again, the base would be e. So I'm going to put this in exponential form. I'm going to write this base e to the y power equals e to the first power, which means y would have to be equal to 1. So when I plug in e, I get 1. So I've got a point at 1, 0. I also have a point at e, which is about 2.7181. So the natural log function is going to look like this, the graph of it. Okay? And we want to evaluate the limit as x is approaching 0 coming from the right. So going this way, it's going to equal negative infinity. Okay, the last one here. I'm going to rewrite this as the limit of x squared as x approaches 0 from the left plus the limit of 1 over x as x approaches 0 coming from the left. X squared, that should be a very familiar function that we are used to graphing. It's going to be a parabola. Okay? As x approaches 0 coming from the left, that's going to be equal to 0. All right? And then if I graph the function this is the reciprocal function. It's going to look like this. Okay? And again, if I look at this function as x is approaching 0 coming from the left, this is going to equal negative infinity. So 0 plus negative infinity, that's going to be negative infinity.